We're going to use an RC circuit to demonstrate the timing in terms of charging a capacitor. So what you have is a time constant, and we're not going to derive this equation. You'll get this in other classes of why this is the case, but a time constant is used to measure how long it takes to fully charge or fully discharge a capacitor. And to fully charge a capacitor or discharge a capacitor, it takes 5 time constants. Again, I am not going to derive this case because you'll get that in future classes, and you don't have the background yet to go through the mathematical analysis to get there. So what do we mean by an RC circuit? Here we have a voltage source that is being inputted to this combination of a resistor, R, and a capacitor, C. And we'll see in a simulation how the output, which is the voltage across the capacitor, fully charges and fully discharges when we turn on and off this voltage supply. We're going to use what we call a square wave to simulate the on and off switch to show the effects of charging and discharging the capacitor. Now, to increase the charging time, you can do it in 2 ways. One is either to increase the resistor or increase the value of the capacitor. And those are some of the ways you can use to increase the discharging time or the charging time of a capacitor. So I'm going to run Multisim to demonstrate the concept of charge and discharge effects of a capacitor. In this case, I have C1 at 1 microfarads and resistor R1 at 100 kilo ohm. We could see that is a variable potentiometer. This RC circuit, where we have the resistor and capacitor connected in series, is driven by this signal generator. And you can choose a sine, a triangle, and a square wave. We're going to use a square wave to show that the capacitor is going to be charged and then discharged with the square wave. This has a frequency of 1 Hertz. It has 50% duty cycle. Okay, let me click on this oscilloscope here. And the oscilloscope shows the one in red, which is our square wave. Okay, so 50% duty cycle implies that it's 50% high at 10 volts, since this has an amplitude of 10 volts. And it decreases to a low at minus 10 volts. So it's 50% high and 50% low. Now what we're going to do is measure the voltage across this capacitor, and this is represented by this orange line. You could see that it takes time to charge up this capacitor, but we get there to 10 volts. And then to discharge the capacitor to minus 10 volts. Alright, now when we multiply 100 kilo ohms by 1 microfarad, we get 0.1 seconds. So that's our time constant. So 0.1 seconds times 5 is 0.5 seconds. And shown here is 1 full cycle of the square wave. So this is 1 second, since this has a frequency of 1 Hertz. And then 1 over the frequency gives us a time period of 1 second. So let's run this simulation. And it's going to take time. Let the computational algorithms take over. And we can see that it's charging and discharge. Notice this is at a resistance of 100 kilo ohms. Now suppose I decrease the resistance. We should get there faster. So as I decrease the resistance, what are we doing? We're reducing the resistance and reducing the time constant. So we're going to get there faster, and you can see the effect of the oscilloscope shown here, that it is charging faster. Okay? And that's the result when it's at 5% of 100K, which is 5K. Let me go to the maximum again, and you could see that it takes time to get there. Now, notice we barely got it because since it's 0.1 second is represented in here in this time constant, and you could see that 100 milliseconds is 0.1 seconds for each division, and that you could see here that it's fully charged around 5 divisions or 0.5 seconds. Now we can decrease the time to charge by changing the frequency. So we can basically double the frequency, which means the period is less, and so the capacitor won't charge. So if I increase to 2 hertz, choose a hertz here, and stop it and start this program again, you could see that it didn't get to the 10 volts or the minus 10 volts. Let me increase the frequency to 4 hertz, so we should see 4 cycles. Let me stop the program and run it again. And let it settle down. And you could see that it's even lower, closer to 5 volts now, before it gets fully charged. So we can change the timing of when the capacitor is fully charged and discharged by either providing more time by changing the frequency to a lower frequency, or increasing and decreasing the resistance. Now I can get there by decreasing the resistance. So let's decrease the resistance, which decreases the time constants, and you could see that it's charging up much faster as well as discharging faster. And then when it gets down to close to 0, you could see that the voltage of the capacitor is following the square wave of the signal generator.